If you drop a glass of water onto a hard tile floor, it shatters into a chaotic spray of jagged shards, sending water splashing in every direction. You have seen this happen 100 times, and your intuition accepts it without a second thought. But you have never, not once in your entire life, seen a puddle of water suddenly pull itself together, leap off the floor, assemble dozens of glass fragments into a flawless cylinder, and land gently on a table. If you drop a sugar cube into a hot cup of coffee, the white crystalline lattice dissolves, dispersing sweetness evenly throughout the dark liquid. Yet you can stir that cup of coffee for 1 billion years, and the sugar molecules will never spontaneously band together to rebuild the crisp white cube. This striking one-way street is what physicists call the arrow of time. It governs every waking moment of our existence. We remember the past, but we cannot remember the future. We watch people grow old, but we never see the elderly grow young again. Buildings crumble, stars burn through their nuclear fuel, empires fall into ruin, and our universe marches relentlessly from a state of pristine structure toward a state of decay. At first glance, this seems like the most obvious fundamental rule of nature. But if you peer beneath the surface of everyday experience and examine the foundational equations of physics, you will uncover one of the deepest and most profound mysteries in all of science. The mystery is this: almost every fundamental law of physics that we have ever discovered is completely time-symmetric. If you write down Newton's equations of classical mechanics, which describe the orbits of planets and the collisions of billiard balls, the variable representing time can run forward or backward with equal validity. If you record a high-definition video of 2 frictionless billiard balls colliding on a pool table and play that recording in reverse, the reversed sequence looks entirely natural and obeys every law of Newtonian mechanics. The same is true for James Clerk Maxwell's equations of electromagnetism, Albert Einstein's general theory of relativity, and even the Schrödinger equation governing quantum mechanics. At the microscopic level, the universe does not care whether time flows toward the future or toward the past. Why, then, does our macroscopic everyday world possess such a brutal, uncompromising directionality? Why can we not unscramble an egg, unmix a drop of ink from a glass of water, or reverse the ashes of a burned book back into crisp pages of literature? The answer lies in a single, subtle, and widely misunderstood concept known as entropy, and the ironclad rule that governs it, the second law of thermodynamics. To truly understand why entropy always increases, and whether it could ever, under any circumstances, run in reverse, we have to embark on a journey that spans 2 centuries of scientific history, stretches from the atomic scale to the birth of the cosmos, and explores the ultimate fate of reality itself. The story of entropy began not in a quiet ivory tower of theoretical physics, but amidst the soot, grease, and iron of the Industrial Revolution. In the early 19th century AD, humanity was rapidly learning to replace muscle and horsepower with the immense strength of steam engines. These roaring machines burned coal to boil water, using the expanding steam to drive pistons, turn gears, and power the factories and locomotives of a rapidly modernizing world. Yet, early engineers were confronted by a frustrating limitation. No matter how meticulously they designed their boilers, pistons, and pipes, a large portion of the energy produced by burning fuel was always lost as wasted heat escaping into the surrounding air. In the 1820s AD, a brilliant young French military engineer named Sadi Carnot set out to determine the absolute theoretical limit of steam engine efficiency. Carnot realized that an engine requires a temperature difference to perform mechanical work. Heat must flow from a hot reservoir to a cold reservoir. In doing so, he laid the foundations of a brand new scientific discipline: thermodynamics, the study of heat, work, temperature, and energy. Carnot proved that no engine, no matter how perfectly constructed, could ever convert 100% of heat into useful mechanical work. There was an inescapable tax demanded by the universe whenever heat was transformed into motion. A few decades later, in the 1850s and 1860s AD, the German physicist Rudolf Clausius took Carnot's pioneering insights and formalized them into universal physical laws. The first law of thermodynamics was already well established: energy cannot be created or destroyed, only transformed from one form into another. The total amount of energy in the universe remains constant. But Clausius realized that the first law was incomplete. If energy is always conserved, Why can you not simply gather the heat that dissipated into the air when a car brakes and use it to propel the vehicle forward again? The total energy would remain identical. Yet our universe strictly forbids this from happening spontaneously. Energy, Clausius recognized, is not just defined by its quantity, but by its quality and usability. Heat naturally and spontaneously flows only from hotter objects to colder objects, never the other way around. To quantify this one-way degradation of usable energy, Clausius coined a new word in 1865 AD, entropy. He derived the term from the ancient Greek word trope, meaning transformation or turning point. Clausius formulated the second law of thermodynamics in words that would echo throughout the history of physics. The entropy of an isolated system always increases over time, or at best, remains constant in ideal, reversible processes. It never decreases. In classical thermodynamics, entropy was treated as an abstract macroscopic property, a measurement of how much thermal energy in a system is unavailable for doing mechanical work. When a log burns in a fireplace, the highly concentrated, organized chemical energy stored in the wood is converted into light and heat. That heat spreads out into the surrounding room, vibrating the billions of air molecules until it is thoroughly dispersed and diluted. The total energy in the room has not changed by a single joule, but the entropy of the room has soared, because that dispersed heat can never be easily gathered back together to perform work. However, classical thermodynamics could only describe what happened. It could not explain why. Why should heat disperse? Why should energy spread out? What was happening beneath the macroscopic veneer of temperature and pressure? The revolution that would finally unlock the true nature of entropy came in the 1870s AD through the work of an Austrian physicist named Ludwig Boltzmann. Boltzmann took a radical, deeply controversial step for his time. He attempted to explain the laws of thermodynamics by assuming that matter is made of countless tiny, invisible, constantly moving particles called atoms and molecules. At the time, many prominent scientists rejected the existence of atoms. But Boltzmann pressed forward, creating the field of statistical mechanics. Boltzmann realized that to understand entropy, one must bridge the gap between two distinct ways of looking at a physical system: the macrostate and the microstate. A macrostate is the overall large-scale description of a system that we can measure with our senses and instruments properties like total volume, pressure, temperature, density, and energy. A microstate, on the other hand, is the exact ultra-precise configuration of every single constituent atom in the system, the specific position, speed, and direction of motion of every single particle at an exact instant in time. Boltzmann's monumental insight was that a single macroscopic state can correspond to an astonishingly vast number of different microscopic states. Consider a simple everyday analogy: a standard deck of 52 playing cards. If we define our macrostate as a brand new, perfectly ordered deck arranged sequentially from ace to king in each of the 4 suits, there is only exactly one microstate that satisfies this condition. There is only one specific sequence of cards that gives you a factory-ordered deck. But if we define our macrostate as a completely shuffled, disordered deck, there are 8 times 10 to the power of 67 possible arrangements of those cards. If you throw that ordered deck into the air and let the cards scatter across the floor, the probability of them landing in a shuffled, disordered sequence is overwhelmingly close to 100%. The probability of them landing in perfect sequential order is not mathematically zero, but it is so unfathomably small that if you threw the deck once every second since the beginning of the universe, you would still never see them land in perfect order. Boltzmann realized that entropy is nothing more and nothing less than a direct mathematical measure of the number of microstates that correspond to a given macrostate. On his tombstone in Vienna, his famous equation is carved for eternity. S equals K log W here. S represents entropy, K is Boltzmann's constant, and W represents the German word Wahrscheinlichkeit, meaning the number of microscopic ways or microstates available to the system. When you understand entropy through Boltzmann's statistical lens, the mystery of the second law of thermodynamics shifts dramatically. Entropy does not increase because of some mysterious cosmic force pulling the universe toward destruction, nor is there a physical law preventing atoms from moving in reverse. Entropy increases simply because of pure, unyielding probability and statistics. There are simply vastly unimaginably more ways for a system to be disordered than for it to be ordered. Think of a sealed glass container divided into two halves by a central partition. On the left side, we place 100 quadrillion gas molecules. The right side is a pure vacuum. This is a state of low entropy because all the molecules are confined to a specific, restricted volume. If we suddenly remove the partition, the gas molecules, bouncing around chaotically in random directions, will rapidly spread out until they fill the entire container evenly. Why do they spread out? Not because they repel each other, and not because they prefer the empty side, but simply because each individual molecule has a 50-50 chance of being on either side of the box. The number of microscopic arrangements where roughly half the molecules are on the left and half are on the right is vastly larger than the number of arrangements where all 100 quadrillion molecules coincidentally cluster on the left. The gas expands because an even distribution represents the macrostate with the highest possible number of microstates, the state of maximum entropy. This statistical realization immediately raises a tantalizing and dangerous question. If the second law of thermodynamics is fundamentally a law of probability rather than an absolute unbreakable microscopic constraint, could we find a way to cheat it? Could an intelligent agent, armed with precise knowledge of every atom, selectively manipulate particles to decrease entropy without doing work? In 1867 AD, the Scottish physicist James Clerk Maxwell proposed a thought experiment that would torment and inspire physicists for more than a century. Maxwell imagined our gas-filled box divided into two chambers, A and B, connected by a tiny, frictionless, microscopic door. Operating this door is a microscopic entity, creature that would forever become known to history as Maxwell's demon. The demon has superhuman vision and reflexes. It observes the individual gas molecules whizzing toward the door from both directions. In any container of gas, at a uniform temperature, the molecules do not all move at the exact same speed. Some move very quickly, possessing high kinetic energy, while others move slowly, possessing low kinetic energy. Whenever a fast-moving molecule approaches from chamber B, the demon opens the door and lets it pass into chamber A. Whenever a slow-moving molecule approaches from chamber A, the demon lets it pass into chamber B for all other particles. The demon keeps the door firmly shut. As time passes through this selective sorting, chamber A becomes filled exclusively with hot, fast molecules, while chamber B is left with cold, slow molecules. The demon has created a temperature difference out of a uniform gas without doing any mechanical work on the gas itself. That temperature difference could now be used to run a heat engine and generate useful energy indefinitely. By selectively sorting particles, Maxwell's demon appeared to have successfully reversed the arrow of time, decreased the total entropy of an isolated system, and shattered the second law of thermodynamics. For decades, physicists struggled to explain where Maxwell's demon was violating the rules. The door was assumed to be frictionless, and the gas was an isolated system. The resolution to this profound paradox did not arrive until the mid-20th century AD, and when it did, it revolutionized not just physics, but the newly emerging field of computer science and information theory. In 1929 AD, the Hungarian-American physicist Leo Szilard took the first major step by showing that the demon must consume information to make its decisions. To decide whether to open or close the door, the demon must measure the position and velocity of each approaching particle. Szilard suggested that this act of acquiring information carries an intrinsic physical cost. The definitive breakthrough came in 1961 AD from German-American physicist Rolf Landauer at IBM. Landauer established what is now known as Landauer's principle. Information is fundamentally physical. Information is not an ethereal, abstract concept that exists outside the material world. Every bit of information must be encoded in the physical state of a physical system, whether it is the magnetization of a hard drive platter, the charge in a silicon transistor, or the neural pathways of a brain. Landauer proved that while measuring and processing information can theoretically be done with zero energy dissipation, the erasure of information is strictly irreversible. In 1982 AD, the American physicist Charles Bennett synthesized these ideas into the complete exorcism of Maxwell's demon. To continue sorting molecules indefinitely, the demon's finite memory will eventually fill up. Before it can process new incoming molecules, the demon must wipe its memory to make room for new data. Landauer demonstrated that whenever a single bit of physical information is erased, a precise, inescapable minimum amount of heat must be dissipated into the surrounding environment. That dissipated heat increases the entropy of the surroundings. When you calculate the entire thermodynamic balance sheet, the entropy generated in the environment by the demon erasing its memory is always greater than or equal to the entropy reduction achieved inside the gas chambers. Maxwell's demon cannot cheat the universe. The second law remains victorious, tightly binding the flow of heat, the nature of probability, and the physics of computation into a single unified framework. Yet, as we look around at the world we inhabit, another apparent paradox emerges. If the second law demands that entropy must always increase, why is our universe filled with such astonishing, breathtaking order and complexity? Look at a single living cell, with its intricate molecular machines, its delicately folded proteins, and its double helix of DNA faithfully replicating genetic instructions. Look at the human brain, arguably the most complex and highly organized structure in the known universe. Look at majestic spiral galaxies, gleaming solar systems, and crystalline snowflakes falling from winter skies. How can a universe governed by an uncompromising law of increasing chaos produce such profound structures of order? The resolution to this puzzle lies in a critical, often overlooked detail of the second law. It applies strictly and exclusively to isolated systems that do not exchange energy or matter with their external environment. A refrigerator provides a simple, everyday demonstration of this principle. Inside a refrigerator, the temperature drops, meaning the thermal entropy of the food and air inside the compartment is actively decreasing. But your refrigerator is not an isolated system. It is plugged into an electrical outlet on your wall. The electric motor and compressor pump refrigerant through coils on the back of the appliance, dumping heat out into your kitchen. If you measure the entropy decrease inside the chilled refrigerator and compare it to the entropy increase caused by the hot air blowing into the kitchen from the compressor, you will find that the total entropy of your house has increased. Living organisms, planets, and galaxies are open systems. In 1944 AD, the legendary physicist Erwin Schrödinger published a groundbreaking book titled What is Life?, in which he addressed this exact question. Schrödinger wrote that a living organism avoids decaying into the inert equilibrium of death by constantly drawing in what he called negative entropy. From its environment, life on Earth is an exquisite engine powered by a massive entropy gradient. Our planet is constantly bathed in high energy, low entropy, visible sunlight streaming from the surface of the sun at a blistering temperature of nearly 6,000 degrees Kelvin. The Earth absorbs these organized high-energy photons, uses them to drive photosynthesis, power atmospheric circulation, and nourish complex food webs. Earth then radiates that energy back out into the cold, empty vacuum of space, which sits at a frigid 3 degrees above absolute zero. Crucially, for every single high-energy visible light photon the Earth absorbs from the sun, it radiates roughly 20 low-energy infrared photons back out into the deep void of space. The total energy entering and leaving the planet is balanced, but the outgoing energy is spread across 20 times as many individual particles. The entropy of the vast cosmos increases dramatically, and it is this enormous cosmic entropy tax paid to the surrounding void that buys Earth the thermodynamic budget to weave the intricate tapestry of life, thought, and civilization. Structure and complexity are not violations of the second law. They are the direct beneficiaries of the universal drive toward higher entropy. This realization leads us directly to the deepest cosmological puzzle of all, the mystery of cosmic initial conditions. If entropy is increasing today, it must have been lower yesterday. If it was lower yesterday, it must have been lower a year ago, lower a billion years ago, and lowest of all at the moment of the Big Bang, 13.8 billion years ago. This fundamental premise is known in modern physics as the past hypothesis. Why was the early universe in a state of extraordinarily low entropy? When we look at the cosmic microwave background radiation, the afterglow of the Big Bang released when the universe was just 380,000 years old, we observe something that seems at first glance completely baffling. The early universe was an almost perfectly uniform, smooth, glowing plasma of hot particles. Every region of space had nearly the exact same temperature and density, uniform to 1 part in 100,000. In a standard box of gas, a smooth, uniform distribution represents the state of maximum entropy. If the early universe was a smooth gas, why do we claim it had extraordinarily low entropy? The answer lies in a fundamental force that we have not yet accounted for in our box of gas. Gravity. When gravity enters the equation, the entire thermodynamic rulebook is turned on its head. In a purely thermal system, without significant gravitational forces, particles maximize their entropy by spreading out uniformly. But gravity is an attractive long-range force. Under the influence of gravity, a uniform, smoothly distributed cloud of matter is extremely unstable and represents an exceptionally low entropy state. Gravity wants matter to clump together, as tiny fluctuations in density allow gravity to pull particles inward. Clouds of gas collapse to form dense stars, stellar nurseries, and massive galaxies. Gravitational collapse releases immense amounts of thermal energy, which is radiated away, driving the overall entropy of the cosmos skyward while creating concentrated pockets of organized matter. The ultimate undisputed champions of entropy in the cosmos are black holes. In the 1970s AD, the brilliant theoretical physicists Jacob Bekenstein and Stephen Hawking discovered that black holes are not just cosmic vacuum cleaners, but thermodynamic objects possessing immense entropy. Bekenstein and Hawking proved that the entropy of a black hole is directly proportional to the surface area of its two-dimensional event horizon, rather than its three-dimensional volume. A single supermassive black hole, such as the one residing at the center of the Milky Way galaxy, contains more entropy than all the ordinary matter, stars, and radiation in the entire observable universe combined. When matter collapses into a black hole, it reaches the absolute pinnacle of gravitational entropy. The smooth, unclumped nature of the primordial plasma at the Big Bang was, in terms of gravitational physics, a state of miraculously low entropy. That pristine cosmic starting condition is the ultimate coiled spring of reality. Every star that shines, every plant that photosynthesizes, every word you speak, and every memory you form is powered by the steady, uninterrupted uncoiling of that initial 13.t billion-rolled low-entropy gift. This brings us to the ultimate question that has captivated thinkers, philosophers, and physicists for generations. Can entropy ever reverse? Could the universe, or any part of it, naturally run backward? Can the broken glass ever spontaneously mend itself? To answer this, we must examine the edge cases of modern theoretical physics. The first place we must look is the realm of pure statistical mechanics, and the profound insight known as the Poincare recurrence theorem. In the late 19th century AD, the French mathematician Henri Poincare proved a remarkable theorem regarding dynamical systems. If you have a closed, bounded physical system with a fixed amount of energy, containing a finite number of particles obeying the classical laws of motion, that system will, given a sufficient amount of time, return arbitrarily close to its initial starting state. Consider a box containing a modest number of gas particles clustered in the left corner. As the particles collide and bounce, they disperse throughout the volume, maximizing entropy. But because their trajectories are deterministic and the volume is finite, every possible configuration of those particles will eventually be explored. If you wait long enough, there will inevitably come a moment when, purely by random coincidence, the trajectories of all the particles happen to aim them simultaneously back toward the left side of the box. For a brief instant, the gas will spontaneously compress itself back into the corner, and the entropy of the system will drop back to its initial minimum. This means that on unimaginable timescales, entropy does not just increase monotonically forever, it fluctuates. The broken glass can, in pure theoretical principle, reassemble itself if the trillions of vibrating atoms in the floor just happen to hit the glass fragments with precisely the right synchronized upward velocity and phase. However, the catch is the word time. The time required for a Poincare recurrence in a macroscopic system, what physicists call the recurrence time, is not millions, billions, or trillions of years. For a simple glass of water or a container of gas, the recurrence time is a number so staggeringly colossal that writing it down requires exponents stacked upon exponents, 10 to the power of 10 to the power of 26 years or more. To put that in perspective, our entire universe has existed for only 13.8 billion years, mere 10 to the power of 10 years. The probability of witnessing a spontaneous, macroscopic reversal of entropy in our everyday lives is so vanishingly small that for all practical and scientific purposes across the lifetime of the cosmos, it is absolute zero. The second law remains an unbreakable statistical certainty for any system larger than a handful of molecules. This statistical reality leads to a famously unsettling paradox conceived by Ludwig Boltzmann himself, the concept of Boltzmann brains. If our universe is simply a random, fluctuating thermodynamic system in an eternal state of thermal equilibrium, then every once in an astronomical eternity, a random fluctuation will temporarily decrease entropy. It could fluctuate enough to create an entire solar system, or a galaxy, or the whole observable universe. However, in the mathematics of probability, small fluctuations are exponentially more likely than large fluctuations. A fluctuation that spontaneously creates a single, isolated conscious brain floating in the void, complete with artificial, fabricated memories of having lived a life on a planet called Earth is unfathomably more likely to occur than a fluctuation that creates 100 billion organized galaxies. If our universe were merely a statistical fluctuation out of maximum entropy, you should conclude that you are almost certainly a solitary Boltzmann brain, imagining this very moment before dissolving back into chaos. Modern cosmologists use this paradox not as an endorsement of Boltzmann brains, but as definitive proof that the past hypothesis must be physically real. Our universe is not a temporary random fluctuation in a dead equilibrium. It is the unfolding aftermath of a genuine cosmic-wide low-entropy birth. What about other cosmic scenarios? For many years, cosmologists debated what would happen if the expansion of the universe were to halt and reverse, leading to a big crunch where space collapses back in on itself. In the mid-20th century AD, some physicists wondered if the expansion of space reverses, would the arrow of time flip? Would radiation travel back into stars, broken eggs reassemble, and entropy decrease as the cosmos contracted? Modern astrophysics has thoroughly dismantled this idea. If the universe were to contract, it would not be a movie played in reverse. As galaxies collide and matter collapses under immense gravitational forces, stars would explode, matter would crash into colossal black holes, and the universe would grow hotter, denser, and wildly more chaotic. The contraction of space would be an era of catastrophic entropy generation, not entropy reduction. Black holes would merge into ever larger monsters, driving the total entropy of the collapsing cosmos toward astronomical, unprecedented heights right up to the final singularity. What about the microscopic quantum frontier? In recent years, cutting-edge quantum physics laboratories have performed fascinating experiments manipulating individual atoms, trapped ions, and quantum bits of information. In these microscopic, highly controlled environments, physicists can exploit quantum entanglement to create situations where heat temporarily flows from a colder quantum particle to a hotter one, or where the microscopic arrow of time appears to run in reverse. Yet, every single one of these exquisite quantum demonstrations confirms the second law rather than breaking it. These microscopic reversals are made possible only because the experimenters are pumping precise laser light, radio frequencies, and energy into the system from the outside. The local quantum subsystem experiences a microscopic drop in entropy, but the macroscopic laboratory equipment, the computers recording the data, and the power grid supplying the electricity all generate vastly more entropy in the process. The cosmic ledger always balances. This leaves us facing the long, ultimate arc of our universe's future. If entropy cannot be reversed on a cosmic scale, where is our universe heading? Astronomers and theoretical physicists have mapped out the deep future of reality, and it is a journey defined entirely by the steady, irreversible climb of entropy. We currently live in the stelliferous era, the glorious, vibrant age of stars. For the next 100 trillion years, stars will continue to fuse hydrogen and helium, illuminating the cosmos and fostering the conditions for life. Eventually, however, galaxies will exhaust their reservoirs of interstellar gas. One by one, the stars will exhaust their nuclear fuel and go dark. Red dwarfs will fade into cold black dwarfs. The universe will enter the degenerate era, populated only by the cold corpses of stars' white dwarfs, neutron stars, and brown dwarfs drifting silently through an ever-expanding, freezing void. Over unimaginably vast spans of time, on the order of 10 to the power of 40 years, even the fundamental building blocks of matter may decay. If protons are unstable, as many grand unified theories of particle physics predict, the solid remnants of planets and dead stars will slowly disintegrate into a thin mist of leptons and photons. The universe will then belong entirely to black holes, the black hole era. For spans of time that defy human comprehension, from 10 to the power of 62, 10 to the power of 100 years, these gargantuan gravity wells will be the only macroscopic structures left in existence. Yet even black holes are not eternal. Through the slow, steady trickle of Hawking radiation, black holes will slowly radiate their mass away into the void, ending in blinding final flashes of gamma rays. Once the last black hole has evaporated into a thin bath of low-energy photons, the universe enters its final permanent chapter, the dark era, and the ultimate state of heat death, also known as the Big Freeze. In this state, all energy has been completely, perfectly, and uniformly dispersed throughout the unfathomable expanse of expanding space. Every temperature difference has vanished. There are no stars, no structures, no chemical reactions, and no sources of usable energy. Entropy has reached its absolute, insurmountable maximum, because there are no gradients, no heat can flow, no work can be performed, and no physical change of any kind can ever occur again. Time itself, in any meaningful physical sense, ceases to exist. Without change, without an increase in entropy, without an arrow pointing from a distinct before to a distinct after, the concept of a clock loses all physical meaning. The universe reaches a state of eternal, motionless, frozen perfection. Faced with this staggering cosmic horizon, it is easy to view entropy as a grim, malevolent force, a cosmic villain, slowly dismantling everything we love, turning stars to ash, and condemning reality to a cold, silent grave. Yet that perspective misses the profound and poetic truth at the very core of thermodynamics. Entropy is not the enemy of complexity. It is the author of it. If the universe were at minimum entropy, it would be a frozen, unchanging block of crystal, trapped in rigid order where nothing could ever move or happen. If the universe were at maximum entropy, it would be the featureless heat death, where everything has already happened and nothing can change. We exist in the magnificent, fleeting, dynamic middle. We live during the golden age of cosmic history, in the brilliant window of time where the universe is making its grand journey from the low entropy simplicity of the Big Bang to the high entropy equilibrium of the deep future. Every thought you have ever conceived, every beat of your heart, every masterpiece of art, every discovery of science, and every bond of human love exists only because entropy is increasing. We are transient, magnificent eddies in the cosmic river of energy, temporarily organizing matter and meaning as the great current flows past us. Entropy dictates that the river must eventually reach the sea, but in the meantime, it gives us the current that makes the entire journey possible.